A person walking at top speed maxes out around 4 miles an hour. But place that same individual on a bicycle and they cruise at 20 or even 30 miles an hour with the exact same physical effort. This occurs without a motor, without a drop of fuel, and without a single computer chip. This mechanical harmony required decades of iteration to refine. Looking at early designs, like the 19th century penny farthing, illustrates the initial, awkward attempts to solve the problem of human locomotion. The question is how this specific arrangement of metal tubes and rubber tires translates a rider's physical exertion into sustained forward velocity. The bicycle serves as a specific physical intervention designed to bypass the inherent speed limits of human biology. The process begins the moment a rider applies force to the pedal. This illustrates torque. The leg applies a straight, downward force, which the crankset converts into a turning force. As it rotates, its teeth grab the chain's links, pulling the assembly forward with significant tension. This patent from 1889 shows the historical roots of the design. This specific method of transferring torque has remained the central component of bicycle engineering for over a century. Torque acts as the essential bridge here, taking biological muscle effort and turning it into a mechanical input. Once the energy is loaded into the chain, it travels back to the gears mounted on the rear wheel. This part of the machine utilizes mechanical advantage, the specific physical mechanism that alters the ratio of input effort to output speed. In low gear, the chain connects a small front ring to a large rear ring, multiplying turning force for inclines. Conversely, in high gear, a large front and small rear ring decreases force, but maximizes rapid wheel rotation for high speeds on flat terrain. Mechanical advantage allows a rider to adapt their limited power to different physical environments without reaching immediate exhaustion. The chain's final task is spinning the rear wheel. As it spins, the wheel stores rotational energy, which helps maintain the bike's momentum over time. If the wheel is simply rotating in a circle, we have to look closer at how that translates into horizontal motion across the ground. Horizontal travel requires friction. At the point where the rubber meets the road, microscopic friction prevents the tire from simply sliding in place. This grip allows for the application of Newton's third law of motion. According to the law, every action has an equal and opposite reaction. As the tire pushes backward against the pavement, the ground pushes the bicycle forward with that same amount of force. The bicycle pushes backward against the road, which forces the earth to exert that same force in the opposite direction, propelling the rider forward. When we observe the full schematic of a bicycle in motion, we see torque, mechanical advantage, and ground reaction forces all firing in unison. The machine acts as a containment system for human power, ensuring every watt of output is applied toward forward motion, rather than being lost to heat or friction. A simple bike ride is an active application of these fundamental physical laws. By isolating and magnifying these principles, the bicycle converts a person's limited biological energy into sustained, high-speed travel with an efficiency that few other machines can match. To keep the momentum going, click the video on your screen to explore another feat of human engineering, and make sure to subscribe so you never miss an episode.